trained neural networks that are in the model, which I expect has very weak relaxations. So we're very curious to hear about it. Without further ado,
no relaxations. Actually, that's the fun part.
Even worse.
So, well, first, has the Zoom link been sent out? Because I did get somebody sent an email asking if there was a Zoom link.
No, so we didn't plan to do it on Zoom. Then we got some requests from people who really wanted to see the recording afterwards.
Oh, okay.
So this way, yeah, we didn't send it out, but we'll be able to send it the recording afterwards. Sorry about that.
That's fine. Just wanted to make sure nobody was left hanging. So yeah, thank you for having me. As Kevin said, I'm talking about optimizing over trained machine learning surrogate models. And yes, this is dated January 15th. These are some slides I gave at an internal seminar at LANL a couple of months ago. Yeah, so what am I talking about here? So the setting is that we've trained a machine learning model and we're using it to make decisions. And now we want to make those decisions in some kind of optimization context. So we've already collected data, trained our model, validated it, and now we're doing something along the lines of design or control or verification of that model that involves optimization. So to zoom in on the optimization problem that I showed in the previous slide, we have a problem with some physics-based constraints and some machine learning constraints, and then equality and inequality constrained. And we're trying to, it's just a standard optimization problem. And in the setting that I'm going to talk about here, it's all going to be continuous variable local optimization problems. So we have, so as an example that you can kind of hold in your head as I'm kind of repeat this mathematical structure, the physics-based constraints are usually something like a model of the power grid. The machine learning constraints are something like predicting some time to failure or some stability index of the power grid that's hard to encode with physics-based constraints and maybe is better represented by data. And then we have, of course, many bounds that are safety constraints and things like that. Okay, so it's a fair question if we're solving decision-making problems with some sort of physics-based component, why we're even using machine learning in the first place. So I'm going to try and motivate that in this slide. And so there are many contexts in which a physics-based model is not well known. So this includes some like semi-empirical correlations or relationships in thermodynamics and other things like image recognition, which can be integrated into robotic applications or other things where we maybe have a physics-based model for one part of the system, but not a good physics-based model for recognizing if this is a 7 or a stop sign or something. So that's the first reason that we use machine learning constraints in these decision-making problems. The second is that sometimes the physics-based model is difficult to optimize over. And so this can be because it's either defined by some black box type simulation that doesn't give you the derivatives that you need to solve optimization problems. Or it could have, in many cases, physics-based constraints have functions like logarithms and fractional powers and all sorts of weird things that can cause optimizers to either converge very slowly or to crash. And so another way to kind of think about what we're doing in some cases is paying some approximation error for a more numerically stable version of our model. So that's this, there's a paper that I'm referencing down here that did this. And then another reason is just that the physics-based model is too slow to evaluate every step of the optimization algorithm, and we need something faster, and we're okay with paying some approximation error for that. Okay, so if I've convinced you that there's some use to optimizing over machine learning models, then there's some use to doing decision-making with machine learning models, then why are we optimizing over them, right? Aren't they like, we already trained them, they're already optimized in some sense. Like why optimize over them again? And so the answer is design and control problems for one, and then second, machine learning, verifying the machine learning model, or proving that it can't.
Sorry about the AC. So it does that, it will go away in a second. So
yeah,
sorry about that.
Mm-hmm. So proving that the model can't make unsafe predictions, with inputs bounded in a certain context. And then kind of the flip side of verification is generating adversarial examples where we're not necessarily proving that the model can or can't, make certain decisions given bounds on its inputs, but we try and find examples where it either satisfies or doesn't satisfy some constraints. And I'm going to consider nonlinear local optimization with interior point methods in this talk. So this is in contrast with a lot of the recent work on optimizing over machine learning models that I've seen, which has been focused on polyhedral relaxations of ReLU functions. And I'm doing this because, well, the neural networks are already nonlinear. I have a very strong statement here in the middle of the slide that nonlinear local optimization is more scalable than global discrete optimization. Maybe some people would disagree about that, but I personally think that's true. Feel free to disagree, but I mean, the more concrete reasons are that we can handle a wider variety of activation functions with nonlinear local optimization, and many physics-based constraints are already smooth and nonlinear. So these two kinds of functions fit together well in what I think is a scalable framework. And so go ahead. Yeah.
Sorry, I'm not an optimization person.
Okay.
Why do we need to be careful about that statement?
So it's the best optimization solvers, the commercial solvers that perform best on and are most widely used in industrial practice are discrete linear global solvers. Mm-hmm. And kind of until very recently, nonlinear optimization or local optimization was only done by a few solvers, most of which were open source and kind of not as reliable in real world settings. So there's kind of a reliability gap between the commercial discrete solvers and the open source nonlinear solvers that I think a lot of people interpret as a performance gap. And so that's kind of the distinction I would make there is that.
But does it matter in this specific setting that you want to optimize over machine learning models, or
does what
this
matters?
Distinction that you have?
Well, it doesn't work in the past where you have a trained machine learning model like in the same framework that is talking about today. But we restrict everything to ReLUs, and then you can model it with integer variables.
Yeah.
And then that's your structure. And then you're like, we can still be optimal within this space. And I think what you're saying here is if we let go of those restrictions and we focus on local optimization, we can actually do way more.
Yeah.
Okay.
And it depends. Like in physics, I think that makes a lot of sense. And some of the applications we have in like logistics, for example, probably less so.
Yeah.
But it's
Okay. Thanks.
That's my 2 cents.
Yeah, and so that line matters because so if you have a really big machine learning model and you introduce many discrete variables for all of the intermediate layers and nodes, then the problem does become intractable fairly quickly. So I don't want to misquote some number, but just it can't handle quote unquote state of the art.
Like that.
Machine learning models. But what I'm going to claim is that local optimization can basically handle state-of-the-art machine learning models. I'll show some examples later. Yeah, and so please feel free to interrupt me at any time. I don't know how much time I'm allotted here, but I'm planning to go like 30, 35 minutes. So, I don't know. I don't need to wear anybody out with too much talking. So just to give another concrete example of a case where we use this, just so when I'm showing all of these optimization formulations over and over, you have some picture to hold in your head. One thing we solve a lot of optimal power flow problems, and these encode feasibility of the power grid at steady state, but obviously the power grid is not a machine that operates at steady state. It's very dynamic. And one of the things that we're interested in is making sure that the dynamic response to topology changes in the power grid doesn't violate certain voltage and frequency limits. And so we train machine learning models to predict, given a state of the power grid and a topology change, whether the resulting transient response will violate a certain constraint and then embed those models into the original optimal power flow decision-making problem. And why we use machine learning for this is that the simulators that we use to accurately and reliably predict the transient response of the power grid to a topology change don't give us the derivative information that we would need to embed them in an optimization problem. So I would love to just embed these simulators into my optimization problems, but they're commercial simulators. They don't give us the information we need. And so we train machine learning models to approximate them and then embed them that way. So I've just given some background, and now I'm going to try and motivate why there's lots of methodological research that can be done here. So, right, if you're convinced that we want to optimize over machine learning models for some reason, why do we need parts 3, 4, 5, and 6 of this topic, right? What is so difficult about this? Why am I up here talking about it? Why is it interesting? So the first thing that's kind of interesting is that supposing you want to embed a neural network in your optimization problem, there are many decisions on how you can embed the neural network into the problem. So if you have like a ReLU function, for instance, you can just embed the ReLU function as a nonlinear, non-smooth max operator, or you can introduce a binary variable that acts as a disjunction, saying which part of the ReLU you're in, or you can use a complementarity constraint to effectively do the same thing. And so that's just one example. The formulation choice that I'm going to focus on here is the difference between adding new variables for every layer and node in the neural network versus composing all the layers into one big function and treating the neural network as a single big complicated function. And this might not sound like it's that important of a change for nonlinear local optimization, but actually this change between having a decomposed function versus a composed function actually significantly affects the trajectory that a solver will take, and in many cases can be the difference between solving the problem and not solving the problem. So just to give a example of this. So what I'm showing is a plot. This is an optimization problem with a machine learning model embedded, projected onto 2 of the degree of freedom variables. Don't worry about what the axis labels are, where one of the problems, starting from the initial point, the circle, makes its way to the optimal solution, the star, in a relatively reasonable amount of time. But the other formulation doesn't do that. It gets stuck over in this weird space on the right and kind of times out, never converges. And this situation is actually fairly common in nonlinear local optimization. This is the kind of reliability problem that I was alluding to earlier. You're not really guaranteed. There are convergence guarantees theoretically, but in practice, the regularity conditions that you need don't hold strongly enough for many practical problems, and so you end up with situations like this quite frequently, where if you choose the wrong formulation or have the wrong initial guess or something like that, your problem won't converge. And so that's why having the option to choose between different formulations of a neural network surrogate model is a nice thing to have. And that's the first thing that I'm saying is interesting about optimizing over these structures. The second thing that's interesting is that if you do a really naive implementation of a neural network model in an optimization problem, it will be very, very slow. And depending on which of the 2 formulations I showed earlier you choose, it will be slow for a different reason. And so, this is just a very simple MLP model classifying MNIST that I threw into an optimization problem for different numbers of parameters. And with fairly reasonable numbers of parameters in the model, we get solve times in the hours. And this is for a local optimization problem. So this should be much, much faster than what I'm showing here. You take some of these numbers with a grain of salt, but this is just if you just throw a neural network naively into JUMP will take literally hours to differentiate through the neural network. Because it's not designed for dense functions and long, large, dense expression trees. And that's what neural networks what neural networks are. I also don't know exactly why it's so slow because there are other AD frameworks that are better. Like if you use ASL, it's actually quite a bit better, but still not great. Anyway, and then if you've decomposed all of the functions and you have lots of intermediate variables and equations and lots of small functions, then you'll get bottlenecked by the linear algebra because you'll have many dense matrices in the KKT matrix, in the matrices that you have to factorize every iteration to solve the optimization problem. And the density in there is just really bad for traditional numerical, traditional solvers for KKT systems, for symmetric indefinite linear systems. And, it'll take, 11,000 seconds to solve some simple problem. Yes.
Can you give more explanation about this full space and reduced space? And you also mentioned here, if you implement with jump, maybe there's also other different implementations.
Yeah. So I'll start with the second question. Yes, there are other frameworks that you could use to do this automatic differentiation. And I recommend you do that. And that's what part of this talk is going to be about, is just don't use jump to do the differentiation through these neural networks. Use something like PyTorch and potentially EXA models. I've heard that it does pretty well. But yeah, you just use a framework that's dedicated for neural networks. The first part of your first question was more intuition about the full space and reduced space. Did you just want to me to define them again, or some intuition about why they perform poorly?
What's the definition of this full space?
Okay.
Reduced space, like if you use two equations to express it's a full space. If you put them together into this one equation, it becomes reduced space.
Yeah, sorry. So I think I forgot to mention these definitions when I showed this slide, but the full space formulation is so you have a neural network model, and then every single node in the network. So it's not just two equations, but for every node in the network, you introduce a variable and two variables and two constraints, or one variable and one constraint, depending on how you count the nodes. But it's just many small equations, each with just a couple of variables that define the network. Versus the reduced space formulation is, the neural network is just a composition of functions at each layer, and you just chain all those functions together into one equation for every output of the neural network. So I write this as one equation. It's one vector valued equation, where every output is just a big, long, complicated expression of every input. Yeah.
Okay.
Yeah. And so that's hard to differentiate. And the first one is hard to do the linear algebra. And those are the bottlenecks.
Thank you.
Yep. Okay. So now I will talk about the first tool that we have developed to help navigate some of these interesting features. Okay, so MathOptAI.jl, it's a Julia package. It's built on top of Jump, and as of very recently has a EXA models backend as well. For integrating various types of machine learning models into optimization problems. And so it's a fairly simple package. We just interface with many different other packages for defining machine learning models. So neural networks and decision trees and Gaussian processes and maybe some other things. And then we define the interfaces that are necessary to translate those models into algebraic form that Jump or other modeling backends now can handle. So just like Jump is, or any algebraic modeling language, is a framework that lets you switch optimization solvers with one line of code. So that's very nice for us because we inherit that benefit. But kind of the point of MathOptAI is to let you switch between different formulations with one line of code. So I'm not going to walk through the syntax, but just at the very bottom, we are adding, we call it a predictor. We're adding a machine learning model to the Jump model. And with one line of code change, we can go from the full space, which is default, to the reduced space formulation. And same with, you can go from a disjunctive ReLU to a complementarity ReLU, or other things like that with a single line of code. So that's kind of why we designed this this package. And because we're encoding all of these machine learning models in a consistent data structure, we can now implement algorithms that take advantage of the structure of these models. So, right, we know which variables are at which layers of the neural network, and we can write algorithms at either the optimization level or the linear algebra level to take advantage of these. And that's what part of this talk is going to be about. So, like I mentioned, the full space formulation is bottlenecked by matrix factorizations, and we're going to get around this bottleneck with linear algebra decompositions. The reduced space formulation is bottlenecked by function and derivative evaluation, and this is very simple to get around. We're just going to run this on GPU using a framework that's actually designed for evaluating neural networks. Okay, so I'm going to go a little bit quickly through these next couple of sections. First, because what we do for the reduced space formulation is not super complicated, won't take too many slides. And then I have a whole talk on the full space formulation tomorrow at this conference, so I'm not gonna go through that in too much detail right here. And then hopefully I'll save enough time to go through an example of putting this all together for some practical example on a kind of interesting problem. Okay, so like I said, to get around the function and derivative evaluation bottleneck, all we do is we offload the function and differentiation to a framework that's specialized for neural network inference and run it on a GPU. It's very simple. The only thing that's slightly less simple is that if you do that naively and you just say, give me the full Hessian tensor of my Hessian second derivative tensor of my vector valued function, my neural network, which is a vector valued function, it's going to be a big third order tensor. And if you just do that naively, get this third order tensor and then sum it up along one of the ranks to compute the Hessian of the Lagrangian, you're actually going to get bottlenecked by that step. So you need to be a little bit more careful and realize that all you need for the optimization is the sum of the Hessians, the individual output Hessians, with their corresponding Lagrange multipliers. So that's the Hessian of the Lagrangian of the neural network. And so we just encode the Lagrangian of the neural network, the outputs multiplied by their Lagrange multipliers, as another layer in this neural network, and we just differentiate through that. And by the magic of forward over reverse automatic differentiation, that's a lot more efficient than evaluating a big tensor and then summing it up. So that's the only thing that is you have to be aware of when trying to exploit efficient function and derivative evaluations for reduced space formulations. Okay, so full space formulations, like I said, we're going to exploit linear algebra, the structure of the neural network at the linear algebra level. I'm just going to show a couple of pictures about how we do this and then gloss through most of the slides. Okay, so the matrix that we solve every iteration of the optimization problem is called the KKT matrix. I'm showing that in the middle. And I have a partition of the variables and constraints where I know which variables and which constraints correspond to the neural network. I'm calling those C. And all we do is we do a sure complement with respect to C. And then once we've isolated C, we can exploit the structure of the neural network. So we have to do some permutations to put it into a triangular form. But we know that neural networks have a lower triangular form, and it's very convenient to represent this with blocks, where the blocks correspond to layers. And they need to have this lower triangular form because it's required for backpropagation through them to work for training. So unless you're doing something interesting and weird with implicit layers, you're gonna have this lower triangular form, and we can exploit that in the linear algebra with block triangular decompositions that don't require that guarantee we won't have fill in for this part of the matrix factorization, et cetera, et cetera. And we can do the KKT matrix factorization and solve a lot more efficiently than if we just threw it to some off-the-shelf solver, which I guarantee you will get bottlenecked by the big dense blocks in this matrix. So I'm gonna skip over that. I guess I can pause here and see if there are any questions, and then I'll get into an example.
So in the reduced space formulation. So the point was to like use something that can do the auto differentiation on GPU.
Yeah.
But why like PyTorch specifically? Is there no like Julia counterparts?
No, there is. You can use Flux, and so I should have mentioned that I mean we have these interfaces built into MathOptAI, so you don't really have to worry about doing that yourself. You just press a button, and we basically do it for you.
Yeah.
Yeah, we use PyTorch just because it's a popular framework that a lot of my collaborators use to train their neural network models, and they give me these models, and so it's just very convenient for me to plug in with it and it works fairly well. But yeah, you can also use. We also support doing the exact same thing with Flux, the Julia machine learning library.
Also depends on like which library the model was built with.
Yeah, basically. Yes.
Okay.
Yeah, and presumably, if you really wanted to use one framework for the differentiation, you could use something like Onyx to transfer your model into that framework. But yeah, we support those two frameworks, and now X models. I've heard X models can do pretty efficient differentiation of neural networks, but I haven't tried it myself. So.
Yeah, just a really quick question. On the subject of topology changes.
Yeah.
I think you mentioned like when we have like a machine learning model, don't we just like have to retrain it to incorporate topology changes?
Okay.
Is there a way to embed it directly?
So the topology changes I was talking about were kind of orthogonal to any of the neural networks. So the topology changes were changes on the power grid.
Okay.
And we used a neural network to represent the impact of that topology change. So it wasn't like a topology change on the neural network.
Okay.
Okay. So the example I'm going to show now is so there's this model that's a graph neural network model for predicting solutions to the AC power flow equations. It's called Canos. And we took this model. There was a recent benchmark of several models for doing this, and Canos seemed to be the best in this recent benchmark. And so I thought, okay, let's try and do something interesting with optimization. I'm going to take this model that some people have put a decent amount of effort into, and see if we can use local optimization to identify adversarial points in it. And I'll define what an adversarial point is in a couple slides. But first, what is Canos? So Canos is a graph neural network model for solving AC power flow. So first of all, how many people here work on power systems type applications? Just a show of hands. Okay. All right, so most. So this is a neural network model for solving AC optimal power flow. And there's been a lot of kind of interest in doing this sort of thing recently for a variety of reasons. There's even a whole workshop going on right now about this. And so I'm putting this up here just to say that this is not some crappy MLP that I trained as like a straw man to show that we could solve big problems and generate adversarial points. This is a model that was developed by some serious machine learning researchers. I believe all of these authors are at DeepMind. And it's like a reasonable amount of effort went into making this model accurate and robust. And so just wanted to justify my use of this model. I wanted to use this to try and solve some optimization problems of various kinds. They didn't release an open source implementation, but luckily this group here at MIT, some of the students of Priyadhanti, released a benchmark library of data sets and evaluation metrics for benchmarking neural power flow solvers, and that included a open source implementation of this Canos model. So that was very convenient for me. I could just take their model, train it up, and use it for my purposes. And then this is a slightly different version of the Canos model, which is trained for solving predicting solutions to the AC power flow equations rather than optimal power flow solutions. Okay. And the adversarial points that I'm solving for are of two kinds. So the first kind is a pretty standard maximum error adversarial point. And so what I'm doing is just maximizing the error between some coordinate of the neural network's output and some coordinate of PF. That's the power flow equations of the output that we get from solving the power flow equations. So it's the difference between the physics-based and the machine learning-based models. I'm maximizing that difference in some coordinate. Here it's the voltage on a particular bus. And this is actually, we don't actually really need constrained optimization to do this, because I could just substitute these outputs into the objective function, and I could find these points with gradient ascent. And that's pretty commonly done in the machine learning literature. But where optimizing over machine learning models kind of shines is when we want to impose some interesting constraints on the outputs to find outputs that not only have high error, but would actually lead to different decisions being made in an operating environment. So what I'm doing here is I'll ignore the objective function and the constrained error for now, but I have the neural network model and the physics-based power flow model. And then I'm putting a lower bound on voltage on some bus for the neural network model. And then I'm constraining the physics-based model to violate that bound by some margin. So the neural network model is predicting everything's feasible. The physics-based model is saying it's infeasible by at least a certain margin. And here I've chosen the margin to be sufficiently high that I think if I can find points like this, that's pretty bad for the neural network, because it means there are points where the neural network says, hey, okay, everything's good, but the physics says, no, you're going to have a voltage below 0.9, which is a very critical, close to a very critical limit in real world power grid operations. These are normalized values. And the objective is really just an exercise in finding these points. So the objective is not so important, but this could be like a minimum cost, or what I do here is I choose some training point and try to find the closest thing to a training point that satisfies these constraints. So here are the results for maximizing error. And so what I'm showing are errors on, this is a 14 bus network, and I'm showing, I've just split it up into two different classes of buses, so just ignore the gray nodes in each plot. For PV and reference buses, I'm maximizing the error in voltage magnitude, and then for PQ buses, I'm maximizing the error in reactive power. And again, these are normalized values of the errors. And so what these plots are showing is that we can find errors of like 6 to 8% in voltage magnitude and up to 4 per unit in reactive power. So that's a huge error actually in reactive power. And in the next couple of slides, I'm going to try and argue that these 6 to 8% errors in voltage magnitude are actually quite significant as well. Okay, so we can find points with high error magnitudes, but the real question is, do these errors actually matter? Do they actually lead to different operating decisions in an actual power grid operating context? So that's what we solve the constrained error problem to try and determine. And so what I'm showing here, what I've done is taken 10 training points. So 10 points that where I know the neural network was fairly accurate. And for each of those problems, I'm trying to solve a constrained error problem on a different bus. So that's what these converged of 9 are. There are 9 different PV or reference buses in this model. And so for each training point, I take each bus and try to find a point that satisfies my adversarial constraints on that bus. So it's a mismatch between the neural network and the physics feasibility prediction on that bus. And the what I'm showing on the right here are the perturbations that are required to satisfy these constraints. So converged is how many of these buses I was able to satisfy the adversarial constraints, and then the perturbation magnitude and zero norm is just the support of the perturbations, the number of non-zeros, right? So the magnitudes of the perturbation that are required to get to an adversarial point. And so what I'm showing here is that in many cases, the total perturbation that we need to make to satisfy these adversarial constraints is in just 2 or 3 variables and with a total magnitude of 10 to 20% of a single variable's value. So I think these are fairly small perturbations, smaller than I was expecting, perturbations that we need to get to satisfy the adversarial constraints from any of these points. And just as histograms, I'm showing the same thing. In most cases, we need to perturb only 2 variables, sometimes even only 1, and by the mode here is about 10% of a single variable's magnitude.
Is X like the load?
Yeah. Thanks for asking that. Yeah, so X it's the inputs to the power flow equation. So yes, it's the loads and the generator voltage angle and generation. Yeah. So it's the real and reactive power for the loads and the real power and voltage magnitude for the generators.
So here the one norm is because I'm guessing the load at buses and like the generation and the generators, these are about the same magnitude, I guess. But here, like for example, like the 0.3 in the one norm, how does that? Because I don't know like your magnitude of like the load or the generation.
Yeah, so the variables are all pretty well normalized. So like loads range from like 0.5 or so to like not that much over 1. So I kind of squint at this and kind of just interpret it as like a percent of a variable's magnitude. Yeah, it's all pretty well normalized.
So for this table, what was the objective of your constraint error problem?
It was minimize one norm.
The one norm.
Yeah. So, I think these results are showing that this model is not robust. If I look at this and I see that, these kinds of constraints can be satisfied fairly close to my training points, I would not want to use this model in any kind of safety critical production setting. So this is all, I don't want to pick on this too much. This is all just, this is kind of well known in machine learning that there are all these adversarial points if you don't do many things to get around them. So this is just, I'm just trying to motivate here that I think a lot of the work in machine learning for physics-based models, should be trying to incorporate robust constraint satisfaction and especially nonlinear hard constraint satisfaction type approaches into their training and inference. So, that's what I'd like to see this used for going forward. So what I talked about is hopefully you guys agree that optimizing over machine learning models is interesting and useful. I showed you that it leads to some bottlenecks and then showed you very briefly how we can get around those. And hopefully I've convinced you that we can actually do this for some interesting real world machine learning models. So that's all I've got. This was funded by several projects at Los Alamos. We have some papers on the topic. You can reach out to me with any questions, and I'm happy to take any questions now as well.
Great, thank you. Questions for us, Peter?
I'm just curious about the scalability aspect more. For example, let's say you're solving optimization over the network, and let's say your network is larger. For example, 8,500 bus or a big city transportation network.
Yeah.
So when I try to solve those, embed that network into optimization solvers, we need to use some sparsity techniques to reduce down the network or consider some aspect of network to reduce somehow its size. Do you think that you can utilize some of that in your formulation?
Yes, if you have some sparsification techniques, we can certainly use them. So So yeah, scalability. I can address the question of scalability to larger power networks in a minute, but yeah, I didn't show any numerical results, but the reduced space stuff is fairly scalable. So the size of the neural network is actually not that important for runtime, as long as, because we're just doing inference, right? So it's as long as inference is fast, then we're good pretty much. So we can solve with like 100 million parameter networks, solve the optimization in like 3 seconds. What this is glossing over is the fact that if the network has a really high input and output dimension, then we need to have a dense block of the inputs by the outputs in the Jacobian, which is going to be challenging for the linear solvers, which I think is what you're getting at, right? If you have like a network that's like 8,000, inputs, 8,000 buses, so that's like 16,000 inputs maybe, then that's not too far from the point at which you start getting memory issues. I think at that scale, you might still be fine. 10,000, 20,000 by 20,000, I think you might be fine with a dense matrix on a reasonable amount of memory. But too much beyond that and you won't be. So yeah, in that case, you would definitely need some sort of sparsification or just running with really big memory machines. Yeah, did that answer was I addressing the right question that you were asking? Yeah. Yep.
I don't come from the energy background.
Yeah.
But what drew my attention was their initial motivation of not using simulators, because the commercial simulators to get the information for the buses and the loads that were violated were not able, you could not differentiate over the results of those simulators. Yeah. So that ignited in my head, like, okay, so if we have like a simulation optimization framework where we usually use a simulator to approximate a surface response, to what degree can this approach be embedded into larger contexts like Frank-Wolf algorithms, where you need those iterations with the simulator, but instead of having the iteration with the simulator, we can just plug in the neural network. So
I think there are two answers to that question. One is, so anywhere you're using a simulator, I don't see any reason why you wouldn't be able to plug in a neural network. They're both functions. The neural network is just maybe a bit like, guaranteed to be differentiable. Okay, not really, but just has some nicer properties. So I don't see any reason why you wouldn't be able to plug in the neural network in settings like that. Of course, the neural network, the one caveat might be that the neural network is almost always going to have a dense input-output relationship unless you do something specific. But I think most simulators probably do also, but maybe don't quote me on that. So the second question is that a good idea? So supposing you can do it, do you want to? So you're introducing some error with the benefit of speeding up your algorithm. And that's kind of a trade-off that I guess is up to you to make. And then the last answer is that there are also some frameworks for sometimes, so for deciding when to use the ground truth model and when to use the neural network model, and kind of iterating back and forth between the two to kind of limit the amount of error that you get. Or try to converge to a solution that holds with the ground truth model without having to use it for every single iteration. So those are called like trust region frameworks for doing exactly that, and I've seen some papers on them, so it might be worth checking out.
Great, thank you.
Yep.
So I want to kind of understand this table. So the objective values are all like constant. This is like the same problem that you're solving, but with different neural network parameters. Is that what?
Yeah.
Okay. So for example, it's like the same case file you're using, but just what are you changing across this? I'm trying to understand.
Yeah, so what's changing is it's a different neural network.
Okay.
The neural network is trained to predict a minimum frequency. And honestly, these networks are, okay, maybe not all of them, but for the most part, these are just complete, like the problem that the frequency that we're trying to predict here is actually a fairly simple function if you plot it. And these networks are really, really over parameterized to predict that value. So so that's why we're getting the same objective for all of these, is because we're using different neural networks, but the neural networks predictions aren't actually changing.
I see.
So like maybe here's another example where like the objective does change with different neural networks. We get fairly similar results. But anyway, yeah, did you have another part?
No, that's about.
Yeah, is there anything
I'm
else?
just digesting it. Okay. So
Yeah, that's why I didn't put these in.
yeah, that's fine. So the iteration count too as well, like the time with respect to the iteration count, like I see, so as we go down in the millions, the solvent time is increasing. I'm talking about the upper half of the group.
Yeah.
The solvent time is increasing, the iteration count is reducing. I don't know. I thought I would expect like when iteration count goes really, really high.
I mean,
That's a good observation. I don't really have an answer for that. My only answer is that iteration count as a function of the problem that you're trying to solve in Newton type methods is like really hard to predict. So it's I don't know why it's so this is kind of odd. I don't know why it's so much higher for the smaller neural networks. It is a little counterintuitive, but you know, that's, you know, Newton methods are, you know, kind of weird sometimes.
Yeah, so I do problems like this, like with Newton method, and I've experienced like the terrible iteration counts.
Yeah.
Although mine is like I'm trying to restore AC feasibility using AC powerful and doing some like jugglery there. So like bus type switching distributed, so like that allows like the iteration counts to reduce sometimes. But yeah, it's not the same type of model. But yeah, it's something I'll probably speak to you about later.
Okay,
Yeah,
definitely.
looks interesting.
Yeah, like normally if I see something like this, I would assume it's because I would assume that if I'm getting these really different iteration counts, I would also get really different objectives, and it's because the neural network's like not trained well, and so it's like making weird predictions. But yeah, I mean maybe it's just they're trained well within a, you know, they predict the same values within a small neighborhood of you know, our operating space, but you know, sometimes we leave that neighborhood and, you know, spend all that time in the weird, you know, part on the right of the plot I showed earlier, stuff like that.
Right. And all this is done on the Kanos or Kanos PF, right?
No, these numerical results are different. These are on different test problems, completely separate from the Kanos thing. Yeah.
I see. Okay.
So how about we stop the public questions here? You guys can talk more offline, and we can thank our speaker one more time. Thank you.